Hello, this video is going to walk you through the chi-square analysis and cross-tabulation. Now, the next assignment after this, or I should say the second part of this chapter 7, is the assignment for this week, which is our t-test. The t-test is going to compare two sets of continuous data. Remember, continuous data is something that you could subdivide. It has a consistent value all the way through your treatment of it. Ordinal data is something that you rank. Tell me how much you like something on a scale of 1 to 10. You can't really subdivide that, in equal measures. So that's what makes it ordinal. Ordinal, just think in terms of putting things in order or ranking. And continuous are like test scores. So we're going to be doing a t-test for the assignment for this week, comparing two sets of continuous data. Now, the chi-square and the cross-tabulation is very useful when you have ordinal data. So the two variables that you're going to be using for cross-tabulation are nominal data, which are the names of things, and then ordinal data, putting things in order. And that can come in handy. So a couple things that you want to look at is you want to see how it's distributed. And then we're going to do a test to see if the differences between the two is significant. And then the third thing we're going to do is see the effect size for how strong the analysis is. All three of those points are important. The reason I wanted to make this video, a couple of reasons. One, there's a mistake in the data file. And two, I wanted to walk you through the basic calculation that's at the crux of this entire analysis. I don't think the book went into it too deeply. It did in the example of the ethnicity example at the beginning of the chapter, but when it went into doing the assignment, it didn't really break it down well enough, I didn't think. So let's go into it. So remember that the chi-square and cross-tabulation, a good example would be, let's say you're flipping a coin and you're comparing how many times it's going to come up heads and how many times it's going to come down tails. What's at the heart of this analysis is how much you would expect it to come out, what the distribution would be. So if you did a coin toss, what you would expect it to be is 50-50, right? There's a head, there's a tail. There's only two options, so it's 50-50. So if you did 1,000 flips, if you were going to do 1,000 flips, let's say, what would you expect the number of heads would be? Well, it would be half, 500. And how many would you expect for the tails to be? You would expect it again to be half, 500 tails. Then you have your subject flip the coin 1,000 times. Now the actual number is going to be different. Usually it is. It's never going to come out exactly 50-50. So the calculation is going to try to tell you if that difference is because of chance alone, right? It's never going to be perfect. Just chance alone, there's going to be a certain degree of variance. Or if you didn't collect the data accurately enough, right? The subject was distracted, there was wind, that caught the coin or whatever. So the statistical test will tell you if it's more likely than not chance, or no, it's not chance, something else happened here. There was some relationship between, the heads and the tails. And then we're going to go into how strong that is. Okay, so keep that example in mind. Heads, tails, you would expect it to be 50-50, yet it's not. Why isn't it? Okay, and that can come in handy. So an example of the book, follow steps 1 through 13 starting on page 101. So what we're going to do is go to analysis, descriptive statistics, go down to cross-tabulations. Now before we do that, because one of the things that we're going to be looking at gender, and I don't like the way I look. Okay, so let's go to variable view. You open up statistics, the SPSS, and you opened up the data file that I sent you. So when you do that, it should come up looking like this. Okay, so let's go into variable view. And under 35 is I don't like the way I look down here, okay? Now, there was a mistake in the original data file in that the author put these in the wrong order. Or he could put it in any order he wants, but it was kind of counterintuitive, and so he switched it, but he didn't bother, or he didn't remember to make the change to the data file. So let me walk you back to how I came here. Went to variable view, 35, where it says don't like the way I look, which is the one we're going to use. Go here under values. Here's values. These three dots here, hit them. And this is what you define 1 through 4 to represent. 1 represents this, 2 represents that, 3 represents that, etc. Now, if you open up this window and you see that these are backwards, where 1 is agree strongly and 2 is agree, etc., make the change, okay? So 4 should be agree strongly. So the way you would do that is if these are wrong, click that number, remove it. Click the next one, remove it. Click the next one, remove it, okay? And then when you add it, these should be blank. Up here, you put in 1, and then the value that you want it to have. Okay, and then hit add, and it'll go in here. Then you go to 2, and write down disagree, hit add, and then you bring them over to this column. So when you're done, it should look exactly like this, okay? This is the correct one. Okay, so I'm just going to click there. Okay, so now we're going to go to Analyze, Descriptive Statistics, Cross Tabulation, and under Rows, look for the variable don't like the way I look. This symbol means ordinal. And when you find it, click it over to Rows, okay? Under Columns, look for Gender, and this symbol means nominal data. And it's going to go into there. The names are going to be boys and girls, okay? And those are coded where, I think 1 is boy and 2 are girls, okay? So then you go in Statistics. Please click chi-square and phi, Kramer's V, okay? That was under Statistics. And then under Cell, go to Observed and Expected. We want both of those, okay? Hit OK. Hit Continue. And then hit OK. I'm going to close out of this because I have already done that. Well, actually, let me reduce this. So this is what I have. This is the output that I have. So this is the explanation that I want to get into in this video, the heart of it. I want you to look at this number up here. This percentage, which is the percentage of the boys compared to the whole, boys and girls, is 49%. So the number of boys is 442. That represents 49.94% of the entire group. And the girls is 443 of the 885, which is 50%, 50.56% of the whole, okay? Now that is very important because just like the coin toss, you can't do anything until you tell me what's the expectation in terms of how it's distributed, in terms of percentage, heads versus tails. And you have to start there. So you can tell me, well, there's a head, there's a tail, so I would expect it to be 50-50. Okay, so here, the number of boys and number of girls is not 50-50. You have to actually count how many there are total, and then count the number of boys there are, and give me the breakdown. So you would expect there to be, no, there are 49.94% boys of the group, 50.56% of the girls. So that's an important percentage in terms of what's expected, okay? So every one of these in your output, you see expected, 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 expected. That represents this percentage. So of the number, let's look at just this one. We have disagree strongly. Then I'll get down here, disagree, agree, and disagree. Let's look at just one. It's the same logic is going to carry all the way through. So in the number of people that responded, okay, to this one question as disagree, you would expect the breakdown to be this, okay? The total number of the respondents here, total number of respondents is, of answers, is 96, okay? You would expect it to be, for boys, you would expect to be 47.9. Why? Because you take the number of, you apply this percent of 49.94 to the number of how many total. Okay, so the total number of respondents in disagree is 96. Apply the 49.94% of it, so you would expect it, that ratio to apply here, and it would be the boys should answer 47.9. Okay, the same thing with the girls. You would expect the girls, because the total number is 96 and the girls represent 50.56% of the whole, you would expect the girls to come up with a number of 48.1. Then you actually do your survey, you collect the data, and you put the actual data here. The count represents the actual number of respondents. Here's 49, 47, I put it here, 49 and 47. So there is a difference between, let's say, boys, what you would expect them to answer as, and how they did answer, how you would expect girls to answer, and how they did answer. Okay, so there is a difference, but now you want to know if that's chance alone. So if you go over here to the Pearson chi-square, this number here tells you the significance. If it's less than 0.05, it's significant. That means it wasn't generated by chance alone. You know, there is a relationship here between the boys and girls, and it represents the general population. So if this number is less than 0.05, this was not because of wind or, you know, the weather or anything like this. If it's less than 0.05, the distribution was attributed to a relationship. Okay, so it isn't quite what would be expected. Something was another variable that contributed to it. And then you want to look down here at the phi, the effect size. 0.129. You do it on a scale of from 0 to 1. Okay, a scale of 0 to 1, and you can tell me whether that's strong or weak, or I should say 0.1 to 1. Okay, so this is actually a pretty weak. Okay, 0.1 is pretty weak, 0.8, 0.9, and then a 1 would be very strong. So a phi value of 0.129, I would say it's kind of weak, between weak and modest. It was very weak. So what's the difference? This tells me that there is a significance. Something happened here. It isn't what I would expect. And the difference between what is expected and what I really encountered is significant enough so that it isn't chance alone. Something happened, all right, where I'm not getting what's expected significantly enough so that something did interfere or something occurred or there's a relationship between the boys and the girls, okay? However, it's very weak. So think of it in terms of taking a medicine. So they did research on a cold remedy, and they compared the results of the cold remedy to a placebo. And yes, there's a significant difference between the group that got it and the group that didn't. So yes, you can prove that your medicine had an effect. It wasn't random. It wasn't the climate. It wasn't wind. It wasn't anything else. Your medicine did indeed have an effect. However, you go into the strength. This is very weak. So it tells me that cold medicine did have an effect. It wasn't just a placebo effect. It did have an effect. However, it's so weak. You know, the average cold might take 2 weeks to run its course. And thanks to your medicine, it took 13 days to run its course. You shaved 1 day off. Big deal. It's hardly worth even making the investment in your pill. So it was significant. Your pill did do something, but boy, it's so weak. Why bother? So there's the difference between significance and effect size or strength. Okay, so I hope this clarified it up. Cleared it up. And chi-square is a very effective tool. Just remember, as opposed to a t-test that compares two sets of continuous data like test scores, it helps you compare two sets of ordinal data. Okay, and your two variables are nominal data and ordinal data, or you can use, under some circumstances, 2 sets of ordinal data. Okay, it's a very nice tool. You don't have to do this as the assignment, but as an assignment, but I wanted to explain it. Okay, thank you very much.